Present today the usage of the skyex package, which is an R package for the entity linkage process. You can find the code here in GitHub in this link, and also some code for installing it in your RStudio is found here. I have already done it and ticked here the skyex package. You can always click here and you see all the functions that we offer. When you click on a function, then you can see the usage, the arguments, the value it returns, so it can help you a bit with the documentation. Okay, I'm gonna load the data now, which already comes with the package. Is the restaurants dataset. It contains information about the name of the entity, the address, the city, the phone, the type of the entity, so if it's American, steakhouses, and then it's the class. If it's the same class here, it means that these two tuples refer to the same entity. Okay, so first we will start with some blocking, which means we're going to group together those entities that show some similarity and they are worth comparing further. I'm going to try, you have to just give the data, the column we want to do the blocking on, the textual blocking, the method, and the maximal distance. In order to know which methods we support, you can always click here, and then you see that we support Levenstein, cosine, Jacquard, Jarrow-Winker, and Q-gram. Okay, so we got 110 pairs, and let's see here what got grouped together. I'm just projecting their names. Okay, so we got almost the same ones, so maybe the blocking was too restrictive. Maybe we want to have more different values there, more comparisons. So I'm going to try Levenstein with maximal distance of 3. In that case, look, from 110 we go to 583 pairs, so a lot more. Okay, let's project their names now. So sometimes we get the same, the entities with almost the same name, or sometimes we get entities that look like they are not the same, for example, Arts Deli and Brands Deli. But in general, we can find a lot more variety in this blocking. Okay, we also offer prefix and suffix blocking, which means we're going to group together those tuples that this column will start with the same characters. For example, the first 4 characters will be the same. Let me project them. Okay. So we get also some entities here that might or might not be the same one, but maybe they are worth comparing a bit further. And then let's try also the suffix blocking, the same idea, but now we check that they end with the same characters. And we got a lot more comparisons, but we got a lot of entities that we're sure that they might not be the same. For example, monkey bar and oyster bar. It's common for these entities to be accompanied by the word bar or restaurant. So be careful with the domain you apply the blocking to be appropriate and to give you good candidates to compare further. So since this wasn't that good, I'm just going to keep the blocks of the Levenstein for our step of pairwise comparison. So the blocking actually gives you pairs. So this is the columns of the first pair and then the columns with dot y of the second pair. So the only thing you have to do now is just pairwise comparison. You don't have to create the pairs. Let's try some text similarity with Levenstein. You have to give the name of the 2 columns and the method. Okay, so when it's the same word, of course the similarity is 1, and then we get here a 0.75, and then lower values when they don't have much in common. We can also use a textual similarity for the address as well, because it was a string expressed. Okay, so we can call it with Jacquard in that case. We can give the columns, and let's see how our method did. Okay, so we get the same when the address is exactly the same, and then in other cases we get a very low similarity. Now for the semantic similarity, we need a Python interpreter to be already installed, or you have to install it, and then you have to create a project, and the path you give it here as a parameter to the Python path, and you have to choose between two methods. One is WUP, corresponding to Wu and Palmer, and the other one is the path similarity. And the columns we want to compare. So let's see how our semantic similarity did. Okay, so they look like good results. For example, Californian and American 0.94, but Californian and French are low similarity. Okay, we have good values to continue. Now we're going to continue with the labeling. We offer two different algorithms. One is skyex and the other one is skyex. The first one needs the labels because it's going to check different cutoffs, and it's going to put the cutoff there where we maximize the F measure, and the other one just checks the patterns in the data and decides where to cut off. So let us put the classes first to our blocks. And then you don't need any weights or scoring function for this. You just have to put a preference. For example, in our case, we want a high similarity of name, high similarity of address, and a high similarity of semantic. And then you pass these arguments, the data, the preference, which column contains the label, and how is the positive and negative class expressed to this function, and then we get the results. So we can get all the classes here that you can just call and attach it to your dataset, an analysis data frame that we can explore further later. The cutoff is at 12 and an F measure of 0.9, which is very good. So if you just want to take now the classes and not do any more analysis, you can attach it to your data. So the skyex now won't use the classes, but just the similarities of the data, check a density of different classes, and also smooth this function with a smoothing coefficient and decide where to cut off. So the skyex has cut off at k of 17, the other one was k12, and then you can just attach the classes again with the same method. Now let's perform some analysis on these results. First, you can plot the result of the skyex. You can see the different cutoffs and where we actually cut, so where the F measure was the maximal. But you can also see the other metrics. Maybe there is another metric that is important for your domain. For example, if precision is very important, maybe you would like to cut earlier, or if recall is important, maybe you would like to go a bit further. Okay, so for the skyex, we can also plot to see the smooth density function, and the algorithm will cut when the first derivative becomes negative for the first time. So it cuts at 17. If you feel that this graph is too raw or too smooth and you want to play with the smoothing coefficient, in our case we use the 2, now let's smooth it further with the 7, for example. We get a more smoother line, but the cutoff did not change. So the data is really showing that it should be cut at 17th skyline. Okay, for plotting the pairs, we offer 2D and 3D. I'm going to first try the 2D with the similarity of name and semantic, showing the classes of the data. And we can see the true positives, true negatives, false positives, and false negatives. And we see here that our problem is mostly with the false negatives. That's where we're making a mistake. But let us use a better plotting, a 3D plotting, which is more appropriate for our case. Okay, so here in this plot we can actually see that we have a lot of true negatives. So our blocking was a lot flexible. We included a lot of cases that we knew they were not worth comparing, but we compared them anyway. But in general, we did good because we got an F measure of 0.9. If you want to change the colors of this plot, you can always just call, for example, color of true negatives, and you want to make them yellow. Call it like this, and you can change the colors. Okay, also, because this plot gives you only one view of this graph, you can also plot them interactively. So in that case, you're going to get this type of graph that you can move it around, and then you can see how your data is and locate problems easily. So I hope you enjoyed this video. Feel free to download the code from GitHub and play with the package, and I look forward to your comments.